Thank you for coming along. You may have seen me from previous shows, such as talking about privileged containers. I mentioned K-Rail. This is K-Rail. So let's jump into it. Cool. So the things we're going to talk about today, I will give you a general introduction. For those unfamiliar with Kubernetes, that's okay. We'll give you enough knowledge to come along for the ride. We'll introduce the general problem that we commonly face from a security perspective with Kubernetes. We'll demo some of the attacks and some of the ways that those can go wrong. And then we'll also introduce the solution for that we were built for ourselves, which is K-Rail. We'll give you a demo of that and then wrap up. Here is your typical Who Am I slide done slightly differently. If you paste that into a terminal, it should spit out similar stuff as normal Who Am I. I'm Sam, confusingly also called Frenchie, Infrastructure Security Engineering Manager at Cruise. At Cruise, we're a company that makes self-driving cars.
And I'm Dustin Decker. I'm a Senior Infrastructure Security Engineer at Cruise.
Cool. And get the important stuff out of the way. Yeah, Cruise, we're building the world's most advanced self-driving vehicles to safely connect to people, places, things, and experiences we care about. And we're hiring. Cool. So similar to the main talk, we'll do the usual test. Who here has never even heard of Kubernetes? Complete background, never heard of it? Give me a big pirate. Yar. Yar. Okay, cool. This is for Ian. If Ian, you're in the audience, I don't believe you. Cool. What about everyone else? Who's maybe used it once or twice, but not super confident? Has, dabbled a little bit. But give me a big yar. Yar. Okay, that's like maybe a little bit more. What about people who've used it a lot, feel pretty confident, operators or maybe even core contributors to Kubernetes? Who's in that boat? Give me a big yar. Okay, I'd say most of the audience so far has been probably in that second camp. And then finally, who's just confused and from the shipping industry, wondering why we're talking about containers? Give me a big yar. All right, one person, great. I'm very sorry, whoever that was. But we'll break it down and we'll give you enough background knowledge for those unfamiliar. So for the shipping industry, you should be along for the ride. So you may have seen something like this when looking at what is Kubernetes. Descriptions such as, it's an open source container orchestration platform for automating application deployment, scaling, and management, with a diagram like that you look at and still have your head scratching at the end of it. So we'll break it down to very, very basic first principles, the only knowledge you really need to know for this talk. Here, we have a nerd. This nerd would like to make a deployment. And so they make a deployment file, which is typically a YAML file, that describes, this is a pod, this is the image that we want, and here's some metadata around it, such as how many replicas we want. And then that deployment is passed on to the API server. And that's how deployments work with Kubernetes effectively. One important note about the threat model that we're thinking about today is that we're not talking about malicious administrators. People who have access to admin the cluster have access to admin the cluster. That's expected. We're also not talking about people who are completely unauthed, right? We're not talking about kernel ODay, Kubernetes ODays or any ways that you can privilege escalate. We're talking about cases where, commonly red teamers who have creds who want to try and break clusters, or most commonly by far is well-meaning developers who are just trying to do their job, who don't realize that they're accidentally deploying something that's insecure. And we want to be able to provide that feedback to them at the earliest point in the deployment lifecycle for them to prevent these security issues. So a little bit more detail, particularly related to how K-Rail works. So what is the API server? Well, it's the coordinator of the system. So it receives this request and then talks to the other moving pieces, such as nodes. So nodes are effectively the servers that you're trying to talk to here. Think EC2, GCE, or any compute really. And they talk to them via a little thing called a kubelet, which is an agent that runs on those nodes and then talks out to the API server for instructions. Once it receives those instructions, affects the change, which is the pods we were talking about before, which is groups of containers with certain configurations, how many replicas you want, the image, and so on. And the power of Kubernetes really comes from the fact that you can run many, many, many nodes. So that's it in terms of the nouns that you really need to know. What are the verbs? What does it actually do? Well, you can think of Kubernetes as a state machine. One critical thing to understand here is that it takes an ideal state and then realizes it using a resource-specific controller. In this case here, we're showing a simplified deployment controller that takes a request and then makes some pods. Pod memes, not dead yet. And then, but it could do other things as well, such as ingress, right? Where it would take an ingress deployment and then pass it to the ingress controller, which would affect change on, say, load balancers, make some ports open, and so on. And one critical step here, which is important for K-Rail, is that there is an admission controller, right? So when new deployments come in, you can check them with a validating webhook or a mutating webhook, and then either accept, reject, or mutate the deployment as appropriate. So with Kubernetes, we have this powerful tool that provides planet-scale capabilities. However, it's very complex, and tiny misconfigurations can sometimes lead to critical vulnerabilities. So really, Kubernetes is the Death Star. In this talk, we hope to demonstrate how a talented pilot can fire proton torpedoes down some of the common exhaust ports, and then also show you a tool to how you can prevent this. Over to Dustin.
Thank you, Sam. So I'll cover some of the security issues that we've seen, give some demos of them in action, and then I'll introduce the tooling that we made to address this. So compromising vanilla Kubernetes is easy, but securing it is difficult. Even if you create the cluster with best practices like role-based access control and mutual TLS between the nodes, there are still some routes of privilege escalation through standard Kubernetes APIs. And we recently released a blog post to cover some of this in more detail that you should check out on Medium, Cruise's Medium. And so some of those APIs that Kubernetes offers for pods allow you to specify bind mounts. And this can give access to the host file system, host networking, which can be used to bypass a security feature, which we'll cover soon, running privileged containers, which is something that Sam and Maya covered well yesterday. And that's not even talking about kernel vulnerabilities or 0 days. So ultimately, these features can result in host compromise or cluster compromise. And when that happens, they can often obtain secrets they need to pivot through the rest of infrastructure.
One quick thing on that image I absolutely love is, who's seen a container like that where you just look at it and it's like, oh, it's a tire fire inside a container. That image was just perfect when Dustin found it.
Yeah, a lot of surface area which can help facilitate these attacks externally. So here's a demo of using host path, or also called bind mounts, to mount the host file system. And it's used to enumerate every process's environment variables, which can often contain secrets. Have you spotted one? There's a private key in there. Another common practice is escalation through a Docker socket that's mounted. This is commonly mounted for building containers using the host Docker daemon. And this is bad because it gives full API access to the host Docker daemon, which can then be used to spin up new workloads and escalate access. And then cloud providers, they take care of many of the basic security best practices when bootstrapping a cluster, but they can also add some surface area for attack. In this example, the GCE metadata API includes a kubemv endpoint, which is used for the nodes to bootstrap access to the API server. So they grab this credential and they ask the kube API server for their node certificates. And the node authorizer in Kubernetes allows a node to access resources that are scheduled on it. So if you request node certificates for each node, you can request all of those resources, such as secrets. And Brad Giesman wrote a slick exploit which automates this process for all nodes in the cluster and gives you all the secrets that you need to pivot your access. Here's the entry point of it, and all it does is it spins up an evil pod, copies his script, which is what automates the process. And that script will enumerate all the nodes in the cluster. It'll grab the credentials from the kubemv endpoint. Then it'll use that credential to retrieve the node certificates. And then with the node certificates, it authenticates as each node and pulls down the resources assigned to them. And then finally, it'll package them up in a nice tar file and give them to you on your system. So let's watch that in action. It only takes a few seconds on a small cluster. You can see shortly all of the secrets dumped out in a directory. So we saw a lot of these issues. Some of them we were familiar with. Some of them the red team brought to our attention. And some of them Brad Giesman brought to our attention when he was contracting for us. So we knew that we needed to solve this problem. We needed a solution that enforces security policies to prevent some of these misconfigurations. Ideally, it should reduce complexity for engineers, or where it can, it increases visibility and helps educate them. And it shouldn't break things that are already running. We don't want to slow down their velocity too much because they're trying to deliver a product, but we still want to have a good impact where we can. And finally, it needs to be easily extensible. These are some security issues that we recognize today, but surely there will be more down the road. And we also wanted to support some operational use cases that can help make the clusters more stable and performant. And there's some prior art too. Many of these projects were started around the same time or a bit after, but none of them today still solve all the requirements that we set out. A common missed requirement is that they support giving feedback for pods that are applied to the cluster, but not higher level resources that ultimately implement pods, like deployments, daemon sets, stateful sets, and cron jobs. Some of them lack a monitor mode, which will run passively and tell you when a policy would have been enforced. And all but the PSP, the pod security policy, lack a flexible way for adding exemptions, which is a very important feature when you have large clusters with diverse workloads. So introducing KREL. KREL is the workload policy enforcement tool that we engineered to solve these problems. And it includes features like telemetry, which enable you to see what is enforced or would have been enforced if you're running in passive mode. It includes many impactful policies out of the box. It has easy and flexible policy exemptions, structured violation data that you can process with other tooling to help you make decisions. And then one of the biggest features is the real-time interactive feedback. And we'll dive into some of these features now. But first, how did we decide the name? Internally, we called it Security Validator, which was descriptive because it uses the validation webhook in Kubernetes, but is too vanilla, and we wanted to use a car pun. So we went to guardrails, but that was taken in several ways by existing security tooling and also a security company. Then we settled on KREL, which is another car pun, and they're also known as Jersey barriers, which are a divider for traffic used in the States. And it has K, which loosely ties to Kubernetes.
That is the closest we'll get to a dad joke in this talk as well.
So how does KREL work? Well, we have a bunch of hackers and nerds, hopefully mostly benevolent hackers, and they want to apply resources to a cluster. When the validation webhook is configured, or a mutation webhook, it'll create an emission review request to KREL, and then KREL will process the context of that request, so the resource specs and who is applying the resource and where it's being applied, and then it can make a decision whether to allow it or deny it. And that comes back in a response from the API server. And this all happens instantaneously, so they get immediate feedback. And the feedback pointed out before is one of the most important features to us. This is what gives real-time feedback to the engineers that are applying deployments to the infrastructure or systems that are applying it. And in this example, they're applying a deployment, which is a high-level resource that ultimately implements a replica set, and then finally pods. And they get feedback as soon as they apply the deployment. In this case, it's denying the request for a few reasons that they're now familiar with.
And that feedback going back to non-security focused engineers is really valuable. You know, mounting the Docker socket is forbidden. They know exactly why it was not letting.
And we ship today with many policies supported out of the box. And when you encounter a violation, whether it's enforced or not, you get a JSON blob and standard out that you can use for processing. So let's take a deep dive through them on what they actually do. So no bind mounts prevents bind mounts, also called host path mounts, which mount part of the host file system into the pod. The no Docker sock mount is a subset of that, used to mount the Docker socket API, which we touched on before. No Helm tiller prevents deploying Helm tiller, which is often an API that provides unauthenticated access to deploy to Kubernetes and becomes accessible from the entire VPC. Host networking is a a feature that allows the pod to use a host networking stack rather than its own. And this is a bypass for the GC metadata API. Host PID sharing allows the pod to use a host PID namespace, and this is dangerous because it exposes a number of kernel tunables, but it also exposes all the environment variables for every process running on the machine. And they often contain secrets. No new capabilities, which is something that Sam and Maya touched on in greater detail yesterday, but this essentially prevents people from adding additional syscalls that they can use to potentially do nasty things. No privileged container, which is a superset of that. It includes all the capabilities and also a bunch of other things. Mutable image reference enforces hash pinning on the images. And this is important because the tags that people often use can change under your feet. And this can be problematic if a malicious image was replaced, or just from an operational standpoint because the software version changed.
And this one's slightly different here, where it's Docker run Tomcat instead of Nginx. Can anyone see what's wrong with this case? Anyone in the audience? Nope. So in 2018, Docker user 123321 noticed that there was no default image for Tomcat on Docker Hub. And so if you Docker run Tomcat, like a lot of people would do, it would actually pull down this backdoored image that Docker user 123321 put up. And it actually was a crypto miner instead of the official Tomcat image that people expected. So that got 5 million downloads over the period of a few months before it was pulled. And so in this case, yeah, trusted image repository, don't pull from public, pull from a trusted GCR instead.
Yeah, generally you don't want your engineers pulling random Docker Hub images and decide to use internal repos instead. So this enforces that. And the request ingress exemption policy is useful if you have an ingress that publishes services publicly. And this requires that they get an exemption ahead of time, so it's whitelisted, and prevents accidental public exposure of applications. And then recently, a few more have been added. Some of these were contributed by other open source users. And the first one, no pod exec, prevents execing into pods. And that might be useful in a production environment, for example. And there's a work in progress operator that somebody is working on that will actually garbage collect pods that have been execed into after some period of time. So once they've been execed into, they are tainted. You don't trust them. And this will ensure that they get deleted and replaced with a fresh one. The default seccomp policy just ensures that you're using the container runtime default seccomp policy. And that's important because Kubernetes actually runs containers unconfined by default for every container runtime. The override image pull policy was an example of an operational type policy that we've added. And we added that because we're bumping into GCR rate limits with GCP for some of the common init containers we used. And so we just overrode the image pull policy to only download the image if it wasn't always already present on the machine. And then finally, empty directory without size limit. This is another sort of like operational reliability policy and prevents the host disk from filling up on the node from tempfs mounts.
It's also worth noting here that some of these policies we added, but some of these have also been added by the community. So we open sourced this tool in October of last year, 2019, and since then we've had a great response from the community. So yeah, thanks to the people who've contributed PRs on this front.
Yeah, and there are a number more in progress right now too. And so if you wanted to add a policy, you have to implement this interface. Policies are written in Go, so you have the full flexibility of Go, but you ultimately need to implement these two methods in it. And this has changed a little bit since then because we've added support for mutating resources as well, if you want to change certain aspects of them as they come in. But it's still pretty much this.
But the benefit of using a Turing complete language for this is you can put in any logic you like. You could say, hey, this is a deployment after 5 p.m. on a Friday. We'll only let it in if we can also query the Domino's API and see that you've already ordered pizza to say sorry to the team, hypothetically.
And here's an example of one of the policies that's implemented. This is a subset of the no host bind mounts policy. And all it does is it iterates through the volumes in the pod spec, and if it finds one that's a host path, it'll add a violation and return that. And these are some example exemptions that you can use. They have several fields that you can specify, and they all use string globbing. And you can specify like this particular resource in a certain namespace is exempt from some set of policies or maybe all policies. So it's very easy to use, and it's actually more flexible than the role-based access control way of enforcing pod security policies. So what you've been waiting for, a demo of KRail. We'll run this kube exploit again with the GCE metadata concealment bypass, which is the host networking flag, but this time with KRail enabled. So we're running that auto exploit script, and immediately it gives a rejection that the host network use is forbidden. So that exploit no longer works. Now back to you, Sam.
Thanks. So we'll share some actual data from our experience in rolling this out. So this is one of our busier clusters with about 18,000 pods when we did the analysis, and that's just a snapshot point in time. A lot of these are transient, very rapidly changing, which makes it hard to do an analysis of, right? If you just dump it once and then have a look, that data is already out of date. So we run KRail in all of our PaaS clusters. This is just one that we picked out, for example. So here is a dashboard. We mentioned telemetry. Across the top there, you can see there's the different policies. Pod no bind mount, no privileged containers, etc. And a red box in that column basically means that they're in violation. The namespaces on the left we blanked out, but this was self-service. An engineer could log in and have a look at this and be like, oh, interesting. Mine is violating on these three. Oh, why is that? I'll go have a look. And then we ran that for a few weeks in monitor-only mode before setting up enforcement. Periodically, we applied some exemptions ourselves in cases where we're like, oh, this makes sense. This should be, doing whatever it's doing. We sat and watched for a couple of weeks. But once we released this, that's when the real magic happened. So when we shared an announcement that we were going to put in place enforcement, but people proactively went and fixed the problems themselves. When provided with the right information and tooling, most devs will do the right thing. And here's a couple of paraphrased comments from team members, which we particularly like. The one on the right there, where we picked up on a particular thing and we noticed, hey, this is a security risk. Do you mind? Is this intentional? And the response was like, wait, what happened? This stupid? Oh, geez, I'm just going to delete that. So a lot of times the operators were completely unaware that these things were were there and they didn't need to be, so they just deleted and got rid of a lot of stuff. That was a pretty big success story. Then once we put in place the enforcement mode, we also provide another dashboard for violations themselves. And so it really only took us about a week to roll out enforcement across all of our production clusters after running in monitor mode and proactively putting in those exemptions, with effectively zero impact of engineering productivity, which was pretty awesome. Excellent. Cool. So to recap, we provided a brief overview of Kubernetes. We demonstrated some of the common problems with the cluster as they are, and then we also some of the security implications that this has. And then we proposed a solution, KRail, that fixes some of these issues. It is open source, of course. We would love for you to pull it down, have a play around, send an issue, or even better, send some PRs. And we've got maybe time for one quick question if someone wants to throw it on Slido or yell out a dad joke in the audience. Alternatively, questions on Twitter later.
Question.
Yeah, question? Yep.
You're saying you have to write the policies in Go. OPA has its own kind of meta language. So you're
I can repeat the question as well if that's easy.
Yeah, go ahead.
Yeah.
I just wanted to know how easy it is to write it. I mean, I write in Go myself, but if somebody's not familiar with it, or that could be a hang-up for a lot of people who are like JavaScript.
For sure, yeah. So the question was, the policies are written in Go. OPA has an alternative. I can't remember what it is off the top of my head. It's
Rego.
What was it?
Rego. Yeah, Rego is the DSL that OPA uses. And that might be easier for some people that aren't used to programming. But it does have a lot of restrictions. Like you can't order Domino's pizza, or you can't query the Kubernetes API for existing ingresses. So the Go provides more flexibility, and for somebody that's used to writing Go, it might be easier as well because you can use the Go toolchain. And if you are familiar, all you have to do is implement that interface that we showed earlier. But it's not for everyone. There's definitely alternative tooling out there to consider.
Yeah. And even if you just want a tool without necessarily adding your own policies, there's a bunch of powerful policies that come by default. So you don't have to write Go, you can just deploy it. For those that do want to deploy, there's a one-liner in the README where you can just try it out on a demo cluster.
Yep, you can always make a feature request for a policy that you want to.
That too, we're pretty quick. Wonderful, I think we're at time, but thank you all so much for listening. If there's other questions, happy to answer in the hallway or on Twitter later. Thanks so much.
Thank you.